So good morning, everyone. Thank you to the Scientific Organizing Committee for giving me the opportunity to present my research on the emerging molecular complexity in the warm gas of young protostars. So first of all, I would like to give a short introduction on hot cores and complex organic molecules. So we detected the first complex organic molecules towards the hot core. So a complex organic molecule is 6 or more atoms in astrochemistry. And so here I will talk about hot cores, but I will also make comparisons to hot corinos. And hot corinos, you just had a talk by Audrey about it, so now I don't have to explain it. However, one of the questions which remains towards the hot cores is how do we reach this molecular richness? And where is this molecular complexity coming from? Also, when we compare hot cores, we see that they are similar to hot corinos and comets, as Audrey showed. So this is raising the question, like, what is the chemical heritage? Do we have like similar reactions, or what are the chemical and physical processes to reach that? So to understand this chemical richness in hot cores, we wanted to study the emergence of these hot cores, to study the phases just before that. And here I give you a brief presentation of the high mass star formation. And you can see that you have a massive dense cores, and then you have the hot molecular cores, and where you have the outflow and this rich molecular emission. And then you go to the H2 stages where you have ionized gas. So here what we want to characterize is this gap here. So for that, we took some sources. We had the Atlas Gal survey where we have more than 10,000 sources where we have high mass star forming regions. So this gives us a good background to extract the most the hot core precursors, and this is what the SPARC survey did. So the SPARC survey extracted 35 protostellar envelopes and studied them with ALMA. So here you have a zoom. First you have the apex observations from the Atlas Gal survey mapping the dust emission, and then you have the zoom in with the 7-meter array and the 12-meter array of ALMA. It's also the dust emission, and you see that some of the sources from the SPARC survey were single down to 400 AU. So these sources are ideal to study them with single dish, where we do not resolve the protostellar envelope, but we are sure that all the emission is originating from a single massive protostellar envelope. And so in these 6 sources, we wanted to study the chemical and physical parameters to understand the emergence of the hot cores. So for that, we did a spectral survey towards apex, with apex towards the 6 sources, and we covered 206 and 6 gigahertz between 159 gigahertz and 374 gigahertz. You have here the transmission, the atmospheric transmission over the band, and you have the frequency coverage that we have. And you can see here that all the 6 sources are extremely rich. So even though they are hot core precursors, we still have a lot of molecular emission. We started publishing this data, and more papers will come out. And if we zoom on a small chunk of the spectral survey, we see that we have differences between the sources. Some are extremely rich, but some have less molecular emission. So we want to study why do we have these differences, and where are these differences coming from? So to put in context these objects, we see that they are rich, richer than hot corinos, for example. However, they are not as rich as Sagittarius B2. And so what did we do to analyze this data? Because we wanted to study the differences and in the physical parameters and in the chemical and molecular composition, we had to use exactly the same method to study all these objects. So first we did a line identification using CDMS and GBL. Then we did the line fitting of all the lines. And then we used the rotational diagrams. Shortly, the rotational diagrams describe the population that you have in each upper energy levels, and you can extract the total column density of each molecule as well as the temperature. And with these parameters, we were able to do some LTE modeling with widths and to estimate the size, the temperature, and the column density. Because we had a large bandwidth, we had to estimate the beam dilution because most of the emission is unresolved. So we had to do some size estimates, and in case we didn't have a satisfactory model, we had to do some iterations between these two steps. At the end, we were able to obtain for all the molecules the line widths, the column densities, the temperatures, and the sizes. And so what did we obtain? So the first thing that we obtain is the molecular diversity in all the objects. And here I'm presenting all the molecules that we detected and also the differences that we have between the objects. And the first thing that you can see is that you have more orange in the deuterated and S-bearing molecules and also in the comps. So the main differences are in these three molecular families. So among the 40 molecules that we detected on average, we have up to 15 molecules varying between the objects. So now I will present you the results that we obtained on the comps and show you the differences that we have between the objects. And if we look at the temperature, which is one of the physical parameters that we obtain, we see that most of the gas is still cold. So here you have the temperatures for all the comps except methanol and methyl cyanide. Why did I exclude these two molecules? First of all, because these two molecules are tracing the cold and the warm and the hot envelope in all the objects. However, you see that for these three objects, the other molecules are tracing only the cold envelope. So most of the gas is still cold. However, we start to have three objects where we have a well-defined warm gas phase. And here we can really see the emergence of this warm gas phase and study how we have the emergence of all these complex molecules that we see in the hot cores. And if we look now at the distribution of the temperature for each molecule in all the objects, we see differences between all these molecules. And first, we see that we have the cyanides, and the cyanides have clearly a gas temperature well above the desorption temperature. So here you can see the desorption temperature with this bar here, and you see that they are all emitting in the red part of the plot, meaning that we should have thermal desorption for all the cyanides. Then we have a second group, which is like methanol dimethyl methyl bromate, and where it's not as clear, and we have the gas temperature in the hot gas, which is similar to the desorption temperature. So for these molecules, we are not sure that they might dissolve through the thermal processes. And then we have the last category of molecules where clearly the gas temperature is below the desorption temperature, and so they should not dissolve through thermal processes. Meaning that to detect them in the gas phase, if they form on the grains, we need non-thermal processes such as shocks or secondary UV photons or cosmic rays. And now we want to see how are the abundances, and we want to compare that to models. So this is a reminder of what we saw just before. And then if we look at all these molecules, we see that for all the cases, we do not reproduce the peak abundances that are given in by the model of ER data here. So this means that, first of all, we cannot differentiate between all the models from our guard, and also we cannot be certain that all the chemical reactions that we see in that they are involved in this model are happening there. But now, if we want to compare to the rest of the literature, we need to go into the physical parameters, because we said that they are hot core precursors. So if we look at the temperature, which might explain the difference to the models, we see that our objects for most of the molecules are similar to hot core inos. So these objects are colder than the typical hot cores that we have in the literature. So on this aspect, we are similar to hot core inos. But when we look at the sizes, it's a different story. So our objects are compact, more compact than hot cores, but not as compact as hot core inos. So we clearly see a difference there, and that we do not have, it's not hot core inos. They are not exactly like hot core inos. So we have just compact hot cores when we look at the size. And if we now want to look at the chemical abundances and see if we are more similar to hot core inos or to hot cores, we see that when we compare to hot core inos, for all bearing species, we are which are indicated in greenish colors, you see that we are similar to the hot core inos. But when we come to the cyanides, this is not as clear. We have a clear difference between the cyanides and for the cyanides, we have a difference between the hot core inos and and our objects. And if we look at hot cores, because they are supposed to be hot core precursors, so what do we see? We see a larger scatter. It's not as clear. And we do not find a good correlation for all the sources. So this means that we cannot say that the molecular abundances in these objects are similar to the ones observed in the hot cores. So we have clearly a new phase, and this comes to a conclusion, which is that we have here the emergence of a warm gas. We found objects where most of the gas is still cold, and we have this increase of temperature, and we can see that molecules are sublimating from the grains. And this new phase of high mass star formation is similar to a large core inol. However, for the cyanides, we have a clear difference, and they are not exactly hot core inols. They all are also larger, and so we can add this new phase here, that maybe we have something similar to an embedded hot core inol. Thank you.